The first nuclear reaction in our series on nuclear reactions is going to involve the emission and bombardment of alpha particles. Before we jump into alpha particles, I want to draw your attention to a couple things that you're going to see on every nuclear reaction podcast so that you're aware of them. You will see the particle and symbol. On each of those, that'll help us to remember what the symbol is when we're writing out nuclear reactions. And we will always start by going through these items. So all of them, all the particles will have definitions, symbols, some descriptive properties, and then also what PPE or personal protective equipment you'd be expected to use if you're handling something that is an alpha particle emitter. All right, so what's an alpha particle? It is a high energy particle that contains 2 protons and 2 neutrons. Okay, so looking at the symbol, this is exactly what we're seeing. I prefer to use the helium because a helium has an atomic number 2, so it has 2 protons, and it has 2 protons plus 2 neutrons is a mass of 4. So I like using this symbol because it shows me exactly what I'm losing or gaining. You can and you will see the Greek letter alpha being used as well, but it doesn't give us as much information. You'll see why that's a little bit of a detriment later. So our alpha particles are the largest particles. They have the lowest energy. They have very low penetrating power, meaning they can't go through material as easily as some of the other particles, but their damaging power is very high. So the damaging power is higher as alpha particles can be absorbed by stable nuclides and then will transform them into radionuclides, which can decay and emit radiation. So that's why the damaging power is high despite the penetrating power and the energy being lower. When you're handling or around alpha particles or something that might emit alpha particles, a few sheets of paper will actually block these. Remember, the penetrating power of alpha particles is very low. A few inches of air will block these particles. Clothing, skin, those will all block the particles. Please don't eat alpha particles. They are harmful if ingested. One of my favorite applications of alpha particle emission is the use of alpha emitters in smoke detectors. So smoke detectors use americium, a radioisotope. It's americium-241. And when americium is in the smoke detector, the decay, when it's emitting alpha particles, is going to create an electric current. So the electric current is going to be traveling between your positive and negative plates. So you have metal plates that are cations and anions, or anodes and cathodes. And so you usually have a current going here with those alpha particles. However, if you have smoke particles, as we see here, the smoke particles are actually going to block the alpha particles from being able to make that electric current. Once that electric current is broken, sound is alarmed, and your smoke alarm goes off, which is kind of a neat application to think, wow, I have an alpha emitter in my house. And this is also just a great time to remind you to change out those batteries in your smoke detectors. Those are lifesavers. Alpha decay or alpha emission is exactly what it sounds like. So you have a nucleus that decays by emitting or losing or getting rid of an alpha particle. So we're getting rid of 2 protons and 2 neutrons, or a helium. The loss of an alpha particle will result in the nuclide losing 2 from the atomic number, 4 from the mass number. This is where having a little table set up becomes very useful, and we'll get into that in 2 seconds. But let's look at what this looks like. So we have a parent with a mass number and an atomic number. And after we emit an alpha particle, our mass number decreases by 4 and our atomic number decreases by 2. And we show where that went. You have to account for those numbers. Both sides, your atomic number and your mass number, need to add up to the same values. If they don't add up to the same values, they're unbalanced. Now we're talking about alchemy rather than chemistry. So On your cheat sheet, you're going to start making a cheat sheet. Get a note card, get a piece of paper. Let's write out alpha emission. And we're going to use that same format that I just showed you, where alpha emission starts with any old elements, with any old mass, and any old atomic number. And it will split into an alpha particle and a new element with a new mass number and a new proton number. Notice that we see the helium written first and the helium written second. It doesn't matter, just make sure that it's included. So looking over at this table that I've made, I am doing a reckoning. I'm accounting for all those protons to figure out what's going on. So in this equation, I'm starting with 92 protons. Check. Okay, this is kind of our line in the sand. That arrow is always reactants versus products. That's where we draw a line in the sand. Okay, if I take 238 minus 92, I'm starting with 146 neutrons. So my mass number is 238. Therefore, the total mass is 238. Looking at our products, I have put a line in the sand here between the alpha particle and our new element, thorium. So let me do a reckoning. I've got 2 protons for helium, 2 neutrons, so a mass number of 4. Looking at thorium, atomic number 90, that's how many protons we have. And the new mass number is 234. So 234 minus 90 gives me 144. Okay? So my total mass here is 234 for thorium, and the total mass of helium is 238. Okay, so again, these two numbers have to match. And if I were to add up my protons, let me get a different color. This one sucks. If I were to add up my protons on both sides, they equal 92. So I've accounted for what was lost and what was emitted. So you might get in the habit of doing that yourself. Let's take a moment and look at the exact opposite reaction. So instead of losing an alpha particle, we're going to bombard or absorb an alpha particle. And that's exactly what it sounds like. It is a nuclear reaction where the nucleus of one atom or a small particle is bombarded with another. In this case, it's an alpha particle. This can result in new heavy elements, so those having a higher mass than their naturally occurring isotopes, or the splitting of a larger nucleus, which we discussed when we talked about those fission reactions where uranium was bombarded and it split into 2 smaller nuclei. The general reaction, we start again with our elements, random element with mass number and proton number, and we're going to add to it an alpha particle. We're bombarding it. So because this element is absorbing that, we would expect our mass number to go up by 4. That's 2 protons, 2 neutrons. And we expect the proton number to go up by 2, and that will give us the new identity of our element. If you're keeping track, and you should be, you're going to want to add to your cheat sheet now. We have an alpha emission and an alpha absorption. Looking at a sample problem for alpha absorption, I'm going to set up the exact same table where I do a reckoning of my protons and my neutrons and my mass to make sure that I have accounted for all of them. So drawing my line in the sand at my protons, I have americium with a proton or atomic number 95, and the helium has an atomic number 2. So altogether, if I were to add those together, I have 97 total protons on the reactant side. Americium has 146 neutrons, so that's just 241 minus 95. That gives me a total mass for americium of 241. And my helium has 4 minus 2 is 2 neutrons for a total mass, that's neutrons and protons, of 4. The overall mass on the reactant side is 245. That'll be important when I'm double checking that I've accounted for everything on the other side. When we bombard americium with an alpha particle, it results in a new element and it results in 2 neutrons that are formed. Okay, so let's do an accounting for this. All right, so BK has 97 protons. Neutrons have no protons. Duh, it's a neutron. So when we add these together, we still wind up with that magic number of 97. So I've accounted for all the protons. The new mass number is 243. Okay, so 243 minus 97 is 146. If I were to add these together, I should get the mass number of 243, and I do. Looking at our neutrons, well, there's no protons as a neutron, but there are 2 neutrons, so the total mass is just 2. When we add these together, we also get 245. So my protons are equal on both sides of the reaction, and my masses are equal on both sides of the reaction. So if you're given a value and you're kind of having trouble coming up with, well, where did those extra 2 neutrons go? Perhaps they were emitted as an additional neutron in that bombardment reaction. All right, that last example that we saw was kind of tricky because you had to know that some neutrons were also emitted in order to balance that equation properly. So just know that we will let you know if there are neutrons produced, and we'll stick to some more simple examples where they're a little bit more straightforward. And this is a great example of that. So here we have gadolinium-150 decaying by alpha emission, and they want us to write the reaction. So we start with gadolinium-150, and if it decays by alpha emission, it is losing an alpha particle. And here's why using this symbol rather than the Greek letter alpha is good, because I can treat this as a subtraction problem. So my mass number should decrease by 4. So 150 minus 4 is 146. And my proton number, my atomic number, should decrease by 2. So 64 minus 2 is 62. Looking at the periodic table, atomic number 62 is samarium, Sm. So this would be your balanced equation. And again, I'm going to double check. 62 plus 2 is 64. They're equal, they're good. And then I'm going to check my mass number. 4 and 146 is 150. So we're equal all the way around. Similar problem here. We're given even less to work with. It's not even a complete sentence. Polonium-218 goes through alpha emission. Great. I can write the nuclear reaction for that. So I'm going to start with polonium, which is PO, and I was told that this has a mass of 218. I don't need to see what the atomic number is. I have a periodic table for that. Polonium is atomic number 84. And if we're going through alpha emission, we're going to lose an alpha particle. So now it becomes a subtraction problem. 218, the mass number, minus 4, the mass of the alpha particle lost, is 214. This doesn't tell me the identity of anything. I need the atomic number for that. Well, originally we had 84 protons. We lost 2 to an alpha particle, so now we have 82. Winner, winner, chicken dinner. That's the number I need, because I look up on my podcast. That's what I'm doing right now. I look up on my periodic table, and number 82 is plum bum, PB, lead. So what I'm showing now, just to double check my work, my protons add up to what I originally had. 82 and 2 is 84. And my mass number adds up to the original 218. So I've accounted for every proton and every neutron that has undergone transmutation. All right, the other type of problem that you might see is a find the missing blah, whatever. So here we're asked to find the missing part of the equation. So we're kind of just working backwards here from the process that we just used. Remember that your mass numbers need to add up on the reactant side and the product side, and your number of protons need to add up on the reactant side as well as the product side. All right, let's get to it. Looking at your mass number, 157 plus 1 is 158. So whatever the missing species is, it is going to have, let's do this actually over here, it's 158 on this side. You can't just plug that in as your mass number because we know that we've bombarded it with 4. Okay, so the total here is 158. We're going to subtract that 4, and that gives us 154. Okay, so 154 is the original mass number because 154 plus 4 gives us 158. Okay, so we know that the mass number is 154. Working backwards, okay, 63 is your total number of protons. Well, we need to come up with 63 protons here. We've already accounted for 2. So the atomic number for this species has to be 61 because 61 plus 2 gives us 63. Looking at your periodic table, It is PM, promethium 154. So this one takes a little bit more brain power, but it's still just the same logic, making sure that you add up your mass numbers and your atomic numbers to come up with equal sides.